Hello. Uh, Thanks for having me, and I appreciate the opportunity. And it's very nice to see so many friends. And so this is a bit of an experimental talk. I don't. We'll just see how it goes. So normally, I mean, of course, I've given a lot of talks. I would maybe have some slides and have a PowerPoint or a keynote presentation. But I'm going to try to give this talk entirely in Adobe Illustrator, pretty much. So we'll just see how that works out. So let me go ahead and share the screen. I, of course, have actually, before I do that, I should just say there are some things I've been up to, but many of you might well know about them. So I had this beautiful piece that was up at the Museum of Mathematics this last fall, and that's on my website, at least some documentation. And then if you haven't purchased this book, I certainly recommend that this is a very good use of $30. So I hope that some of you will take that offer up. The opportunity to purchase this is full list price. And but it is a good book. And but meanwhile, I just would like to share what I would like to talk about today. So this I don't feel was really adequately represented at the trimester. So I would like to just sort of touch on a theme. So you can see my screen here. Let me hide some of that stuff. The Zoom stuff. Okay. All right. So this is in mathematics. This is Adobe Illustrator, which I think most of you know, have heard of at least. Adobe Illustrator is essentially an interactive PostScript editor. So the most important thing that Illustrator does is allows us to basically to make PostScript images. So let me go ahead and describe what this is. Let me hope I didn't mess this up. Oh no, I did mess this up. Okay. So so we might mean by what we might mean in the mathematical illustrating mathematical community by illustration, I think first of all might be simply illustrating our ideas, like actually trying to render mathematical ideas in some sort of relatively realistic manner. So certainly that's a big preoccupation here. But another thing that many of us in this community, many of you are involved with, is actually studying this as a practice itself. Perhaps like what are the parameters of what can be illustrated? I would certainly, I can think of lots of examples of this, but for example, all the progress that's been made in ray marching and strange geometries, or I guess that's a great example, perhaps. And and then of course in this community there's like lots and lots of people that are actually, including myself, of course, that are doing this using essentially by programming tools. And another thing though that I would just like to mention is that visualization itself is something that many people actually use. So visualization is, of course, a form of illustration, I guess, in a certain sense. But within, let me turn off Discord real quick because it's probably bothering everybody. It's bothering me. Hang on just a sec. But illustration, uh, sorry, just to me. Okay. Illustration, visualization, like famously, people like Bill Thurston worked completely visually. And I think in low dimensional topology and maybe some other disciplines, visualization is a really key tool. But I don't actually mean any of these things. This is not what I'm talking about. I don't mean illustrating ideas necessarily as the end goal, at least in today's talk. I mean, of course, I do this all the time myself. And I really don't mean looking at illustration as a discipline. And I really want to focus not on using computer programming as a tool, although that's central to my work in many respects. And I don't mean just simply using visualization within one's mind or even on paper necessarily as the tool. What I really mean and what I'd like to discuss today is this. It's handmade contemplative illustration. So actually the process of making something by hand, spending lots and lots of time on it, starting over, starting, again and again, and in this manner, actually using that as a research tool. Because really, I think this is sort of underrepresented in our conversation, and yet it's absolutely core to the way that I work. And I think that largely, judge from what I can tell on the tiling listserv, it's the way most people on the tiling listserv perhaps work. And so, and I'm not sure really what other disciplines are amenable to this kind of work, but certainly it's important to me and to others. So I'd like to just sort of demonstrate a little bit about this. And the way I'd like to do this, organize this talk, is to just take a few themes of things that I've explored over a long time. There's no way I can actually show you in any kind of systematic way the work that I've done, but and I'm not really trying to impress you with taking the fanciest things that I could possibly have worked on, but rather I just want to take some um, a couple of basic things and um, sort of also demonstrate how to use Adobe Illustrator at the same time as make the talk. So if you notice on the right, you'll see that my key presses are being recorded. And this is actually to be able to show you really how I have used Adobe Illustrator. I think undoubtedly several other people here on this use this tool, but maybe not everybody. And while I'm doing this, you might notice that there's a kind of a phenomenal number of key presses. I'm using a lot of hotkeys, and I think I'm going to stop sharing just for a second to give a little editorial comment about that. So I'm left-handed, and I used to draw and paint and well, not paint really so much, but certainly draw a lot, and used to be able to write like handwriting. I used to be able to actually spell things out without dropping the pen. Adobe Illustrator has left my left hand kind of in a claw-like form. This is literally what this program, this is really a serious thing. All of you young kids, it's not too late. Hotkeys will literally destroy your hand. I can no longer write. I can't even sign my name. And yet, it's a fantastic program, and I probably would do it again. So you can make your own, but nonetheless, I wouldn't have done it again if I'd not done, if there was an alternative. The alternative is to not get so good at hotkeys. So in any case, here what I'm doing is I'm drawing a shape, which is I call it the L tile. It's often called the chair tile, and I'm showing how you can make a copy of it um, out of smaller copies of it, or form smaller copies into a larger copy, or whatever you wish to say about it. So in this manner, I am um, creating essentially a substitution tiling. And this is, more or less what I do all day long, by many days. That's why, again, I can't really write or hold a pen anymore. And so my question would be, just sort of starting from this interesting structure, what could we say about the kinds of things that we could do? So really what I do with something like this is I would start making these pictures, and then I would end up with something like this. Now, if you have this would be a good time to take a screenshot if that Zoom stuff is not in the way, because if you do take a screenshot, you might be able to participate with me on this next thing that I want to do. So let me get the mouse out of the way. If you do take a screenshot, and you are able to paint in regions, either in Photoshop or a program like Procreate or something of that sort, uh, then you can see like this is, or you can print this out and do this by hand. But um, one thing that, just experimenting like basically a kid would experiment, sorry, and just coloring things in just to see what they might look like, you can discover all kinds of amazing things. So, for example, I didn't know until the other day, actually. I've colored these things a lot over the years, but I just realized the other day that, for example, there's this beautiful coloring. Oops, sorry, sorry, X group. Okay, where you can actually shift these cool things over. And so in this manner, you can see all kinds of subsymmetries that really weren't sort of visible before. You see that this is sort of this periodic structure within there. I'm not going to have time to go through this in much detail, But this is the kind of thing that one can really experiment. And let me just say what these colorings are. I think this is quite an interesting thing to think about. In a regular pattern, sorry, in a familiar periodic pattern, we're used to the idea of subgroups of a supergroup being illustrated by a coloring pattern. Really, what this is it depends on what, I mean, we have to be really clear on what we might mean. If there's the larger group, the group that's finer that has more stuff in it, which is of the uncolored business, then we have this kind of relationship where the other colors, just to use the technical language, which if you've had abstract algebra, great, and if you haven't, it won't make any sense. But we're coloring by cosets essentially, and the relationships um, in this thing are essentially that of cosets, but they're no longer of sort of in a periodic fashion, but in a sort of an irregular way. Let me just show you a specific example of what I mean. So this was something I was thinking about back in '94, I think, and still find this file very interesting. So here, for example, are three, instead of having one L shape, we have three L shapes, black, gray, and white, and three separate substitution rules. As you can see, they each go to have a gray in the middle, and then what's around them depends. Black has three blacks around, gray has three whites around, and white has whatever. And when we do this, we see much as we would see for colorings, we see this amazingly interesting structure. I mean, I think it's pretty interesting. So this is a completely understudied thing. Nobody really has studied this at all, to my knowledge, of these kinds of substitution structures. But in a practical way, this particular one I found especially fascinating. So here's a piece of the tiling. I've used this in so many different ways, but but I just think it's really quite appealing. And one thing that's interesting that I'm going to talk a bit more about because I'm basically um, I'm going to be demonstrating how just basically all these files showing the same kinds of ideas over and over again in different kinds of formats. Really not to show you the ideas as much as to show you the working method. And whatever my working method is, I've applied it a lot to the following observation, which is that if you kind of squint a little bit, the shape in white and gray is exactly similar. Well, not really, but in some sort of, if we could take it to some sort of limit, is similar to the shape that's in black. Let's take another look at that. And again, my point here is not so much to show you these ideas, is just to show you a whole bunch of files, and then and again, the working method is what I'm up to here. So let's see. So here's um, yeah, so we're going to skip that for the time being. We'll come back to that. So here's an idea that when I first actually moved to Arkansas 30 years ago, I was exploring. Here's the same kinds of tiles, but this time we have them in two different orientations, 45 degrees from one another. And notice that because of this tree-like structure, check it out, they interlock beautifully. Isn't that cool? And so I've always really wondered what I can do with this. Can I make, for example, a single tile that would be in some similar fashion interlock with itself, kind of a similarity monotile, if you will. So let me just show you a few more pictures of this. This is the same kind of phenomenon again rendered, but this time as little arrows. If I close these files, this will all speed up, so I think I will. Um, let's see. Oh, here's my partner, my wife coming home. Let me just, so I'm on giving a presentation. And by the way, the fridge is open. I didn't get up to fix it. That's the same thing. All right. So let me show you back up a little bit. So here's another version of the L tiling. And one question that I've been spending a lot of time on in my career is how do we make these L tiles? Can we actually force the structure of these L tiles? Now, by the way, sorry, this L tilings. You see, we can't just have unmarked L tilings and expect to have any kind of structure at all. If I take a unmarked L tile, it can tile in lots of ways, including periodically. And so, but on the other hand, if we return to this, let's see if I get rid of all of this stuff. It's kind of amazing, but this structure here is basically, no matter how I slide it over, let me try my best, something is going to be wrong. Let's see. And the reason for that, let's see, I've probably killed it. Uh-oh, better not take this too far. But the reason that not everything can possibly line up is really very simple. In the so you can see that whatever's going on here, it's kind of scrambled no matter what. Okay, so but the reason for this is very simple. It's just that any individual L, like if I take any individual L tile, and I guess I'm not going to be able to do this very effectively. Basically, the structure, I'll just simply leave it at this, that the structure has this infinitely hierarchical structure where things are larger and larger things that cannot slide on top of each other. Any slide would have to slide something much larger on top of itself. And yet the L tiles themselves can't enforce that. So what I was been interested in for a long time was, a long time ago, was making tiles that would somehow force this structure to appear. And so here's a pair of, I call them the trilobite and cross, but then there's also later the trilobite and crab, and I might show you some of those pictures as well. That these tiles, when they fit together, can only form the L tiling structure. Here I've not really filled in all the tiles, just the what I call the trilobites because they have three lobes, but not in the same way as the animals. These lie in the same pattern as the L tiles, and I think it's quite a beautiful structure, quite a beautiful drawing. So when I said what I wanted to say about this, though, was that the process of drawing this is not incidental to the process of discovering these tiles and working with them. It's absolutely essential. And so one of the reasons why my computer is choking so badly is that among the files that I have open are some very tremendously large ones, which are basically just me farting around doing what I'm doing right now, which is in this. And this, I guess, if there's one real point to my talk, I'm not just rambling and showing you all this old work, although that's definitely part of it. The real point of my talk is to say that this is a key part of what mathematical illustration has to offer mathematics, at least within the limited domains of areas where you can actually learn a lot of stuff by dragging things around and making the drawings. And this really is, I mean, this is why I have a broken hand. I mean, not broken, but a damaged hand, crippled hand. And it has been worth it to me. But nonetheless, I think in an ergonomically better way, this can be a very effective tool, maybe inspiring some of you to consider working in this manner. Again, in tiling, I think that pretty much when I look at the tiling listserv, which is a fascinating and wonderful place where people from all sorts of backgrounds who like tiling come to meet, it seems like the one thing that we mostly seem to have in common is an ability to, or an interest in actually drawing this stuff. So here's something that I learned from doing this. This is unfortunately a huge file, like I was describing. But is if we change the shapes of the tiles and the way that they match, we can get all kinds of interesting behavior. So for example, these are based on the Robinson tiles. The famous Robinson tiles discovered in 1971 have this shape, where the markings can only meet, you see there's one kind of marking that has no sidedness and another kind of marking that has a sidedness. And we can experiment by what happens if we, change this all up and have some, like how effective of a tile could this be? And this is again the point of this talk. My real point here is not necessarily to explain any of this or to show it, but just simply to show you some of my working files and endlessly make the point that this is a valid and effective way to work, really, as long as the computer doesn't crash, which significant concern at the moment. Let's give that a moment. I hope we get through this talk. I might have pushed it. I hope not. Okay, the next time we get control of this, I'm gonna have to oh please. Okay, great. So then I'm closing that file right away. Don't save it. And I'm going to close some more files right away. Okay, so here is sort of a summary of what sort of was pulled out of that file. And you can see that. So for example, if we have the both all the tiles have these markings and it's extremely rigid. Oh no, it isn't actually. It looks like you see there's some sort of weird disruption. You can see there's squares upon squares, but larger squares still, but then along this diagonal, something is terrible has happened. And in fact, that seems to be the case. Honestly, I've kind of forgotten. I guess the point is that there's actually ways to slide these patterns along these fault lines, and that must have been what I was exploring at the time. Notice that everything is looking good to one side of this gray stripe in the middle and not on the other. And this one here, I don't know that this is very widely known, but this is a real result that's kind of, I think, relatively interesting, which is that for people that really know aperiodic tiling, uh, this one on the left is the Robinson tiles, and they have these kind of weird ability to slide. And just this modification and the modification is see that this blue marking here is not got a parity, and here it does have a parity, then suddenly it's a much more rigid thing. I mean, uh, again, this is the point. The point of this is that the working method is to actually draw this stuff in Adobe Illustrator in that big file that just almost crashed the computer. So, so, but then this is, my obsessions never really let up. And so I'm still thinking about this. This is some drawings from quite some time ago showing what would happen if we take going back to this idea that we might have a single tile that could be somehow there's these two structures. One is 45 degrees to another, and yet and scaled by root two. And if we overlap them, you can see that there's quite a lot of interesting stuff. So here, what this is, if I take let's see. So this here is just a single. I don't think that was a very effective thing to do. So never mind. I was going to say that you can't really quite see in this picture, but this is like a grid of squares on squares on squares, but then another duplicate one turned 45 degrees. Here you can kind of see, if you turn your head a little bit, you can see that this little corner is squares on squares on squares, and then the other one is just turned 45 degrees. And again, this particular version of the project never really came to fruition, but the point would be to find, is there some sort of way to take chunks of this stuff and call them tiles, and then the tiles can only form these structures. And there's not enough actually here to do that. But I did want to show you in this great big file, there was, oh, this one that really I like a lot. So occasionally, you get something that I think is just appealing in its own right. But again, this also shows the idea. So this tile in the middle here, maybe that's the one we're looking for. I'll come back to this question in a bit. So I'm going to close this before it in hopes I'm not going to crash anything. Oh yeah, this is white lovely. This is the same idea again. So this is squares on squares on squares, but then again, two of them turned over 45 degrees. And I just think it's really pretty. So where did this all go? Many years later, I guess this must have been around 2016, I started experimenting with these tiles. And again, and this is actually something that I prepared as a kind of a, it's prepared as a group activity, but maybe it's just a fantasy that anybody would actually do this as a group activity. But it has the idea is that you could mark on this thing and sort of figure out what the structure is. And the real key is that these tiles here, which look just the same as the previous ones, but yet now this one has the markings going both, say, horizontally and vertically, as well as diagonally, somehow overlaid. Um, these guys actually start to self-assemble, which is quite interesting in the sense that self-assembly algorithms and in non-periodic tiling is there's a great deal to say about it. And yet this one is a fairly simple one that will self-assemble pretty well up to a certain size. So in particular, in this activity, if you lay down these like this, if you lay down one row of pieces on the bottom, then all the other pieces are absolutely forced from then on to at least fill out this square. And again, this is the real way that this work is done is pretty much what I'm showing you right now. So why don't I show you what these look like? I mean, they're really crazy objects. So like, but the way that I showed you when I was first constructing an L tiling, I do basically the same thing for this kind of stuff. You know, it's just a matter of being careful and meticulous and building it up piece by piece. I'd just like to show you a little animation of something. This is from that same kind of work, and um, this is showing slightly different. This is with an additional component, and this was done programmatically. You can see that these tiles are each being placed in such a way that at any given moment, only one tile can be placed at any given spot, any place there's a green spot. And what's happening here is that the tiles are actually forced to form these larger and larger hierarchical structures. But the real key is those colored lines that are starting to appear are actually this kind of signaling mechanism, which is carrying all of that out. This is kind of a counter example to what I'm just saying, because this was not drawn. So back to this. So right now, when I was in Paris, I was having a lot of fun drawing up something. This is a little much to explain in any kind of detail what this is about, but this is a typical working file. You can see it's quite a big chunk of mess, and it represents probably 20 hours or something. And I'll just say a little bit about it, though. It's kind of a cool idea, I think. Um, well, I guess that really isn't enough time to explain very much of it, but basically, the idea is that the in these little these tiniest circles, the tiniest ones you see are different colors. And the colors that they actually encode the colors for the next size circle up in a very simple way that I don't have time to really explain. And then the next size colors up, they encode indeed the colors for the next size up and so on. And so basically the upshot is that the smallest layer here, the smallest level here, already contains enough information to encode the entire hierarchical structure. I guess I should back up. I should explain to you that individual triangle, each individual one has a blue one and a light blue one and a dark blue one. And the question would be how do I encode this whole hierarchy of like how these guys are stacked up? Like from the little tiny ones, how do I know that it's inside of a big blue one, for example, a big light blue one in some sort of systematic way? And this isn't really the place to explain how that really works, other than to say that it's possible. And um, what these guys are, wherever it might be, you see, that's the downside of having so many files of this kind. There they are, is this crazy business. So, think of it what you may, but one thing for sure is it's a lot of work. So, I mean, just in terms of the detail work of, you see, it's really quite meticulous. And I'm seeing all kinds of things that could be improved, but I don't know. It's like, I think many of you know my work and know the kinds of stuff I do. And if you knew that I spent dozens and dozens of hours just making sure that these colors are right, I don't know if that is something you would have guessed or not. But this is very, very time consuming work. I think it's lovely too. I really like a lot of the details here. So this I won't really try to explain what this was about, why I was doing that one in recently. But here's a question which is a actual question for you to try to answer. So, and this is sort of inspired by some work that I saw at ICER, at the IHP. So, is there a way to take a single tile that, um, when you, this is essentially really close to the kinds of questions I've been asking, because this would allow us to make these kinds of interlocking lattices like I was just showing you. So is there a single tile that you could have two copies of it? One is scaled by, root two and maybe turned 45 degrees or something. And they have exactly the same tiling pattern as these squares with octagons. So maybe it's something like, you know, these are where the tiles would fit. Um, and maybe we would allow, some to return. Maybe it'd be kind of convenient, to instead of insisting it look like this, to insist it look uh like that, but that's the same, but like that perhaps. And the reason that I'm really asking would be what I'm really asking is there an aperiodic similarity monotile? Could one come up with a single tile that um, can that has two sizes that then together those two sizes, sorry, the scaled up one and the regular sized one together would form an aperiodic tiling of the plane, perhaps on this kind of a grid, but then this the way that these hierarchical tiles are arranged with that. And you know, I mean, this is how steeped I am in this. I mean, this is the way I attempted to answer the question, was to construct such a thing really explicitly by just simply taking octagons and hexagons and adding and subtracting in some systematic way from each. This one kind of does it, but I think really that can't be the real answer. I think that I really must mean that I want to have it be turned 45 degrees because from that the two tiles be arranged in something like this. And I don't know, maybe by the end of this talk, somebody will have the answer for me. Um, I have not really spent a lot of time on it, but I would really like to know. So that's sort of one long theme of just to sort of take a little tour through some files. I mean, obviously, this is just a tiny, tiny fraction of what I might be able to show you. So I'd like to just take another one though, just since I can. Since we have a little time, I'd like to show you a little coloring trick, which is also leads to some interesting stuff, and it'll allow me to do some demo work. Um, so I would normally just construct this by hand, but now it's got this cool little hexagon tool. I've been using Adobe Illustrator long enough though that that was a novelty in its day. Whoops, undo this. Okay. And all right. And now I want to take uh, a tiling, the hexagonal tiling, and I want to do this, but I want to look at a subgroup of the structure of this. And this is right back to this idea of sort of coset coloring. So I'm going to take an index 3 subgroup, and it'd be a little easier just to draw it in the first place. See, so I'm going to take an index 3 subgroup. That's to say just a coloring. Um, in the following manner. Let's see, I'll probably have to do this a couple of times to get this right. So I'm sorry, I should have just done it this way. Okay, so that's another thing. This kind of backtracking even is pretty much the norm. Figuring out how to actually do the drawing is a big part of the process. And so typically I might go back and forth many, many times before I actually come up with a process that's going to work. Okay, so what I want to do is pick an index three subgroup, and I'm going to just, that is to say, a three coloring of the tessellation. And okay, and then I want to take then I'm going to take its cosets, which if you are, okay, there's this whole business about right and left and normal and whatnot, and I don't really want to get into that. But basically, what I'm going to do is it's just a shifted copy. That's to say, a right coset if we're multiplying successively on the right, a right coset of the coloring. I just have this as the same coloring. It's just shifted over and then, sorry, the same chunk of colors just shifted over and then colored. Now, if you notice, however, that there's now uh, a third of the colors are still available, and lo and behold, they form a hexagonal lattice themselves. And this hexagonal lattice can itself be three colored in just the same way that the original hexagonal lattice could be three colored. So I could, for example, take um, the, let's do this. I'll take this three coloring, and I can color it like that. And I'll take the other one and I can color it like that. And now I've got a way to fill in these curves. Okay. And lo and behold, the remaining part, which I must have made a mistake just now, the remaining part, that's it. Then the remaining part, lo and behold, I didn't draw very much of it, but it's going to form a hexagonal lattice as well. So this is a great, which then can be repeated in the same manner. So let me just quickly set up a hexagonal grid. This is really a lot of fun to try to do for yourselves. So I'll just make this and you can take a screenshot and fill it in if you wish. Um, sorry, let me just get this done. Okay, so, and so the question might be, well, what do you get if you repeat this process? So here's the hexagonal lattice. I guess you can all make your own hexagonal lattice. If we repeat this process, we get this incredible thing, which I just love. This is essentially like cosets of cosets of cosets. It's a kind of this nested tree thing, and it's these two interlocking lace these two interlocking tribone patterns. And just to sort of show you the kind of messes that I think about is, okay, can you make a set of tiles that then would have to force those kinds of things? This is a totally failed experiment. It doesn't work at all. So no point in actually dwelling on it. But these kinds of hex substitutions have been really on my mind for a long time. This is a this particular thing is absolutely notorious. It's been discovered many, many times. It's the basis of the Taylor-Sokol tiling later. It's has all kinds of things, ways to gussy up its structure to make it into an aperiodic monotile or aperiodic set of tiles, but this by itself doesn't work. And but it has sort of some similarity to the thing I just showed you. But I just want to show you, you know, how these kinds of things manifest over time. So here is a beautiful, this was proposed as a floor actually, but it actually is a proof as well that, or if you will, a demonstration that these cannot be an aperiodic monotile. This is essentially the same structure. And anyway, I can just go on and on. It seems like this is a fine place to stop. Here's the same thing rendered again in this is an aperiodic set of tiles that again has the same kind of structure. I mean, I guess I think I've made the point, which is that, you know, this is a good tool and it deserves a place of recognition. And I hope that others outside the tiling community at least might think about ways to use this kind of work. Like actually, again, the point being that it's not so much that we're illustrating an idea or that we're trying to visualize an idea or that we're studying visualization. It's rather that this process of contemplative, slow, methodical drawing, and at least in my case, and I think many people, as I said, in the tiling listserv community, find to be an extremely valuable and productive and essential mathematical tool. So I think that's a pretty good place to stop. And thank you for your attention. And that was a very experimental talk. So thanks for your patience too.
I enjoyed the use of Illustrator. I hope you felt like the experiment was a success. Um,
That's for you all to decide. But anyway,
People
uh,
can render their judgments in the Discord. But we do have a couple minutes if people have questions. Um,
I see Frank asked a very valuable question, and I don't know. I mean, I assume there must be a lot of research on low vision applications, but I don't really know anything about it. It seems very conducive to that just because it's scale dependent. It's not scale dependent.
I see
think
also
it can
that,
be a good tool because it's SVG to make tactile illustrations as well
Oh yeah.
with CNC. Um,
Yeah, right.
I see that
Jim,
Jim Prop's hand is raised. Jim, do you want to unmute and
Yeah. Um, mentioned very briefly that you've had hand damage from using this tool.
uh-huh.
Um, so I'm wondering to what extent I should be concerned about my workflow, which these days is OmniGraffle and a lot of typing, and I'm not having trouble right now, but maybe 20 years from now I'll
So,
regret what I'm doing.
well, 20 years from now, that's great, Jim. I'm looking forward. I think the problem is key presses. I think that if you think about it, keyboards were not invented for, I mean, keyboards were just kind of, we fell into them. And the old mechanical keyboards worked very differently than computer keyboards. And so the thing that's really damaged my hand, that's why I had the thing on the side, you could see how much handwork I was doing. And it's all, if you really notice, it was a lot of Option A, Shift, Control C business and crap like that. And my feeling is that having two fingers on the keyboard at the same time in the same hand is a mistake.
Mm,
Like that's like I stopped like doing as much of that as possible. It really made a difference.
mm,
But I don't know, just my message, I mean, my message is to you, Jim, but really it's to those kids. Please save your hands.
Well, it's interesting. The demos usually show what's on the screen, but we cannot see your hands.
You
With,
can't see
with,
my hands.
yeah.
Oh, but you did see the key presses, I hope.
I kind of did, but they'd be much more salient if I got to see your hand actually moving and
Yeah.
pressing down on something.
I mean, I'm fast. I'm really good at it. And I've really also paid a price.
Mm,
So, and I might make the same choice if I had made a choice,
mm,
because I've also gotten a lot out of it. I don't know. I miss drawing by
yeah.
hand.
I mean, this ties in with another theme which goes far from what illustrating math is about, which is the idea that tools that enable us to do things quickly can lead to problems like de-skilling. Like I use a lot of ChatGPT these days, but I notice that I'm not quite as good at certain kinds of things as I used to be because I outsourced them. So there's all these questions about long-term effects on us from the choices we make about what tools to use. So I've been thinking about that a lot.
Well, if you go off in a spaceship, you're going to get radiation poisoning. I mean, it's kind of like, I mean, these tools are like amazing. They take us to new places that are incredible. But, you know, I don't know. It's just what it is.
well, we've reached the top of the hour.
Oh, but
Maybe we,
Paul is right. Yes. Yeah.
what's that?
Just to Paula's point, absolutely. Using a tablet is much better. And so nowadays, that's a possibility that didn't exist. But yeah, thank you
Yeah.
very much. And
Um,
I don't mean to take more time.
yeah, well, feel free to continue the conversation and have further questions on Discord and whatnot. And Chaim, you can answer at your convenience or leisure or never if you want. It's up to you. But we should adjourn. we've reached the top of the hour. So thank you all for coming. Thanks to our speakers today, and stay tuned. Hope to see you next time.
Thanks. See you later. Bye-bye.
Thank you.